Howdy class. So today we're going to be talking about ions, so electron configurations of ions instead of neutral atoms. Monoatomic ions, meaning that it is made up of one atom. Those monoatomic ions are prevalent in chemical compounds, so you'll see them a lot in the future, and you probably know of a lot of them. For example, good old table salt. Sodium chloride is made up of two monoatomic ions, sodium ion and chloride ion. Writing the electron configurations for ions follows basically the same rules as writing the electron configurations for neutral atoms. So we can apply almost all of the same rules that we used before. There's like one little exception that I'll show you later. And we can predict the most likely ions that are going to form from certain elements based on their group number and their electron configuration. So here's some examples. Group 1 elements tend to form +1 ions, almost always, if not always. Group 2 elements tend to form +2 ions. Group 16 elements tend to form -2 ions, and group 17 tend to form -1 ions. So that is because we have 18 groups on our periodic table. So group 18 is our noble gas, and group 16 is 2 away from the noble gas, so it's a -2. And group 17 is 1 away from the noble gas, so it's a -1. So why do we keep going back to the noble gases? Because of the electron configurations. So I'll show you. Ions and atoms with the same number of electrons are called isoelectronic. So the most common monoatomic ions that we're going to see, the ones that follow those rules we just talked about, +1 ions for group 1, +2 ions for group 2, those are isoelectronic with noble gases. And they want to be isoelectronic, have the same number of electrons as noble gases, because noble gases have full electron shells. That is the most stable configuration of electron configurations, is when the electron shells are all filled, when there are when we are at our noble gas. So, for example, we can look at our periodic table. This version of the periodic table, I apologize, has the old numbering. So instead of 3A, 4A, 5A, they're 13, 14, 15, 16, 17, 18 is where our noble gases are. So the +1s are our group 1s, like I said. +2s are our group 2s. And that's because to get to a +1 ion, we have to take away 1 electron. And we take away 1 electron from sodium, for example, then we're going to have the same number of electrons as neon. So sodium ion is isoelectronic with neon, a noble gas, and that's why it commonly forms this +1 ion. Same thing goes with our anions over here. Remember, cations are positive ions, anions are negative ions. Fluorine is 1 away from neon, so if we add an electron to fluorine, it'll have the same number of electrons as neon. It'll be isoelectronic with neon. We have to add 2 to oxygen to get it over to neon, and that's why we see the -2s or -1s in our group 16 and group 17 elements. And if you look, there's something funny here because hydrogen can actually be both. So this is why hydrogen is kind of weird. It acts like both the group 1 elements and sometimes like the group 17 elements, because hydrogen, if it's a positive ion, is just going to go back towards nothing. It's going to have no electrons, which is super, super stable. or it can add one electron and be isoelectronic with helium and be very stable as well. So hydrogen's fun, it can do both. And then these are some other common ions. You don't need to memorize the other ones. Aluminum you might want to memorize. Aluminum is always going to be a +3. The other group 13 elements don't always play by that rule, but aluminum always does. So there you go. These are some common monoatomic ions. They all have one atom of that type of element. And this shows how, well, it shows the common forms of these ions, and it shows, or you can deduce from it, that they're isoelectronic with the noble gases. All right, so here's a practice question for you guys. You should solve this. You can pause the video and try it yourself. It's a good practice instead of just watching me solve it. But here we go. So which of the following are isoelectronic? So that means they have the same number of electrons. So let's find out how many electrons these have. So argon is number 18 on the periodic table. So it has 18 electrons. Easy enough. It's a neutral atom, so it has 18 protons, and it has 18 electrons. Chlorine is number 17 on the periodic table. So it typically, so if it's an atom, it would have 17 electrons. But this is a chlorine -1 ion. So we had to add an electron to get to the chlorine ion, the chlorine anion, I should say. So we have 18 electrons here too. Cool. So far, A and B are isoelectronic. What about oxygen? Oxygen is number 8. So the neutral oxygen atom has 8 electrons. But we are the -2 anion, so we had to add 2 electrons. So oxygen has 10 electrons. It's not isoelectronic. Oxygen is isoelectronic with neon, one of our other noble gases, but it's not isoelectronic with argon. Okay, and what about potassium? Potassium is number 19. So the neutral atom would have 19 electrons, but we have the positive cation. So to form a cation, we had to lose an electron. So if we lost an electron, that's 19 minus 1 electron, gives us 18 electrons. So A, B, and C, A, B, and D are isoelectronic. They all have 18 electrons. Oxygen does not. Cool. Let's keep going. So your book doesn't show it this way, but I'm going to show it to you this way. Think back to our ionization energies we just learned in section 4.5. Sodium has a low first ionization energy. That means it's easy to remove 1 electron. It doesn't require very much energy. And that is why sodium and all of the other group 1 elements are typically found as +1 cations. It comes back to their electron configuration. And you can see it here. So if we use box notation, we've got sodium has 11 electrons. So it has 2 in the 1s orbital, 2 in the 2s orbital, 6 in the 2p orbital, and then it's got 1 extra 1 in the 3s orbital. So now that we know that atoms would prefer to have noble gas notation, they prefer to have the electron configuration of a noble gas where we have this nice, beautiful full shell, the N = 2 shell. We can tell that, that sodium is going to want to form a +1 anion and get rid of that electron. So now it's gone. So sodium is isoelectronic with neon. It has 10 electrons and is isoelectronic with neon when it forms the +1 cation. So it's related to ionization energy, it's related to electron configurations. That is how we can predict the charges on typical ions. What about if we remove another electron from sodium? Sodium has a really high second ionization energy. It's really hard to remove that second electron. See, we had this beautiful filled 2p subshell, and then we tried to take one off. That required a ton of energy compared to this one, almost 10 times as much energy. So that means that sodium is not found as a +2 cation. It takes a lot of energy to remove that additional electron. So it's not likely for sodium to be found that way. So that's why we're typically going to find sodium in all of our group 1 elements as +1 ions. All right, now let's consider something else. So magnesium, on the other hand, has a low second ionization energy. We can look here, we've got ionization energy 1, ionization energy 2. We'll talk about ionization energy 3 in a second. So it's easy to remove that second electron. So it's not especially easy to remove one of these because it doesn't change the energy very much. It doesn't get us to a noble gas configuration, but it's not terribly hard. But what is really nice is taking away both of those electrons so that we once again get down to our noble gas configuration. So magnesium 2+ ion is once again isoelectronic with neon, just like our sodium 1+ ion. So again, it comes back to ionization energies and electron configurations. What happens when you try to take a third electron away? Is magnesium going to be found as a +3 ion? No, that requires a ton of energy over here. It's 7 times as big, 7 times as much energy as it required to take the 2 away, to take another one away. So that means magnesium is not typically found as a +3 ion. It would take a lot of energy, and nature doesn't supply it with that energy. So you don't find magnesium as a +3 ion out in the world. You can make it, but you'd have to supply a bunch of energy, see? Those are the main group elements, so now we understand why group 1 and group 2 have a +1 and +2 charge, typically. Let's talk about transition metals, or the D block, as your book likes to differentiate a little bit between transition metals and the D block. Let's look at iron. Iron has a low second and third ionization energy. So that means that it's easy to remove the second and third electrons. So it's not like magnesium. It doesn't stop at +2. The +3 ion is just as likely to happen because it's still pretty low energy. There's not a big energy jump like there was for magnesium. So we can look at that from this electron configuration standpoint. So here is iron. Iron has a electron configuration of argon 4s2 3d6. So it's got the 4s2 and 3d6 electrons in its highest energy orbitals past the noble gas configuration. So we're going to focus on those. So one thing that your book notes and that you should always remember with these transition metals, when they form ions, we take away the 4s electrons first. So when we were doing our orbitals, when we were filling them in the first place using the Aufbau principle, we put those 4s electrons in there first before we went to the 3d electrons. We're going to do the same thing when we take them away. We're going to take those away first. So it might be counterintuitive that you would want to take the 3d electrons away first because they're the ones you added last, but no. Just try to remember that you're going to add the 4s electrons first when you are writing electron configurations of neutral atoms. But when you're writing the electron configuration of ions, especially transition metal ions, you're going to take away those 4s electrons first, or 5s or 6s, whatever. Wherever you are on the d block, you are going to take away those s electrons first. So we get rid of those, we take them off, and now we only have, we don't have that extra shell of electrons. So those two 4s electrons were further away from the nucleus than the rest of the n equals 3 shell, the 3s, 3p, and 3d electrons. So now we don't have those anymore. So we can shrink down our ion a little bit and have lower energy for these electrons to make these orbits. But look at this. So here is our iron 2 plus ion. It has an electron configuration of 3d6. It's happy because we got rid of those bigger 4s electrons. But now we can do one further. If we take away this one, so it ends up over here, look at what we got. We got a half-filled subshell. We got that beautiful half-filled D subshell. That is more stable than if it has 4 electrons or if it has 6 electrons. The 5 out of 10 D electrons are very stable. It's very nice when we have half-filled subshells. So that's why this ionization energy, the third ionization energy, is also fairly low for iron. So because the ionization energy is low, it's pretty easy to remove both the second and third electrons. So iron is likely to be found as either a +2 or a +3 ion. It just depends. They're both pretty equally likely to be found in nature. All right, so let's do a practice question. What is the electron configuration for the cobalt 2 plus ion? So CO is cobalt. So looking at my periodic table, cobalt is number 27. So let's see. So that means that cobalt, if I read across my periodic table, cobalt is going to have an electron configuration of argon. It's going to have a noble gas core of argon. And then we have 4s2 electrons. And 1, 2, 3, 4, 5, 6, 7. 3d7 electrons. So that's where we're at for cobalt. So you can check it because argon has 18 electrons. If we have 2 in the 4s orbital, that's 2 here, and we have 7 in the 3d orbitals. So that adds up to 27. Check. So this is cobalt, the atom. So now we want to write the configuration for cobalt, the ion. So we have 2 places we could take our electrons away from. We're going to take those higher energy electrons. So we're not going to touch the core electrons. That's going to stay the same. So it's between the 4s electrons and the 3d electrons. And like I just told you, we always take away the 4s electrons first. And that's because we put them there first, we take them away first. Try to remember it that way. So we're going to get rid of those. And if we got rid of 2 electrons, that gets us to a +2 ion. So the electron configuration for for cobalt 2 plus ion is just argon 3d7. We got rid of those 2 4s electrons, and that means that we're at a +2 ion, and this is what we have left. So when you're writing these electron configurations for ions, you want to start with the neutral atom and then decide where the electrons are going to be taken away from. Okay, awesome. So let's stop here and then we'll start another video.